Okay, so last class we have discussed some of the steps of the Pso algorithms. Okay, and we'll elaborate more on this Pso algorithm. So next is the geometrical illustration of Pso. So how the particle is moving in the first space. Okay, so that is basically geometrical. It is explained. We'll see that how it is basically explained. So first is that the update velocity for particles consists of three components. We know that any updation of the velocities, we know that velocity.
Excuse me, sir.
Yes.
Your screen is not sharing.
Oh, yes, screen is not sharing. Just a minute. Huh? Now?
Yes, sir. Now okay.
Okay. So the update velocity for particle consists of three components. So what are those three components? One is the inertia component, that is the first component, that is the personal at least the velocity at which the particle is moving. Second is the personal experience, and third component is the social experience. So these are the three components of the velocity. Now consider a movement of a single particle in a two-dimensional subspace. So here you see we have a particle. The initial position of the particle is xi, and it is moving with a velocity vi. Now when this particle is moving with a velocity vi, it has some random direction. So let us say it is moving this way, then it is moving this way, then it is moving this way. So after the one iteration, the particle has moved to this particular position. So that means this is the position, this is the new position. So this is your new position. So new position, how it is, how the particle will move. So it is from the xit to xit plus 1. The way of the path they are taking, this is the path actually. Okay. So the new velocity. So we know the new velocity, it is equal to the new position plus this particular velocity. Okay. So this is the new velocity, that is Vij t plus 1. So Vij t plus 1, we know that how to calculate this Vij t plus 1. Vij t plus 1 is basically Vij t plus C1 into random 1 into P based minus Xij t, and then plus C2 into random number into G based minus the Xij. So that is the basically three components we have. We know that particular equation. Now next is then the particle will move in this search space. So the base position of the neighbors, it is G based, for example, and this is the personal base of that particle, P based. So this is your cognitive velocity and this is your social velocity. That means the particle has started from this particular position. Now, when all these particles are moving in the search space, so they have found that in the first cycle, the personal based position of that particular particle is P based, and among the group it is G based. Okay. So every particle will try to achieve their own personal best. So always they will calculate the difference between their own personal best and the initial position, that is xi. Then the group based from the social experience, this is the G based minus the initial position. So this is actually every particle will always try to move towards the group based direction. Okay, because there is a group based. So after time step t plus 1, it was actually the positions are coming this way. This is the xi part. That means the position of the particle. This is the initial position. This is the position after t plus 1. So at t plus 1, there is a velocity component, that is vi t plus 1. Then this is the xi t plus 2. That means after second iteration, Then this is the G-based and this is the personal based at t+1. So every cycle, there will be a personal based, there will be a global based, and there will be a velocity and there will be a position. So these are the four components: xi t+1, bij t+1, G-based, and p based j t+1. So these are the basically four components which is actually governing the movement of the all the particles. The figure illustrates how the three velocity components contribute to move the particle towards the global base position at time steps t and t+1. So you see at time step t equal to 0. So these are the position of the every particle. Let us say there are within that subspace, the location of the particles, they are located. This is the fashion they are located. Now let us say that particular cycle, the G-based is, this is the red one is the G-based. So all these particles, they will try to move at this particular location. They always will try to move at the location of the G-based. So next at time step t equal to 1. So there is a small movement, a few movement of this particle towards this G-based position. So now in the t equal to 0, G-based was located here. But at t equal to 1, G-based has moved to here. So this is the global base on that particular cycle. So the particle will try to move at this particular location. So this way they will actually basically move forward and finally they will actually reach to the G-based or the global based. And that is the basically optimum value of the particle. So we'll skip this thing. Now next is the advantages and disadvantages of the Pso algorithm. So what are the advantages of the Pso algorithm? First advantage is Pso algorithm is derivative free algorithm. So I think if you have done the Lagrangian multiplier technique, so there we have seen that we need to take the first derivative of that particular Lagrangian function. So there are some functions which is non-differentiable. That means we cannot differentiate those functions. Okay. So in those cases, if we have to take, if we have to solve those functions, so then it is very difficult with the help of classical technique. Why we are taking this top computing techniques? There are certain functions, there are certain problems which we cannot handle with the help of some conventional or the classical technique. So there we need to take some artificial intelligence technique or soft computing technique. Those techniques will be very much useful because the computation time is less and we'll get the more accurate result. Second is that it is easy to implement so that it can be applied both in scientific research and engineering problems. So the application part, it is a wide area. Every engineering problem, it is not like that only electrical engineering problems this Pso algorithm is applied. It is applied in every discipline, every engineering problem, even at the scientific research also. Now third is that it has a limited number of parameters and impact of parameters to the solution is small compared to the other optimization technique. So in this case, we have seen that the parameter tuning is it is a very hazardous task, okay, in any optimization technique. So if you have to tune the parameter at a repeated interval, so that will be very much difficult to basically understand. So we need certain things which is actually that will basically make the algorithm parameter free. So this Pso algorithms, we don't need to tune any parameter. So that is the advantage, most advantage of this particular algorithm. So the calculation in the Pso algorithm is very simple. So we have seen that there is a very simple step. There is a two algebraic formula. These two, one is the velocity updation and then second is the position updation. So these two formula is basically describing the whole algorithm. So if we can understand those two formula, what is the velocity formula and what is the position updation formula, then it is very easy to implement this particular algorithm. There are some techniques which ensure convergence and the optimum value of the problem calculates easily within the short span of time. Okay. So the convergence speed of this particular algorithm, it is very faster. So it will take a very shorter span of time. And that's why the implementation part is very, very much easier compared to the any conventional technique. Now, Pso is less dependent of a set of initial points than the other optimization technique. See, this is the initialization. See, when we have to start this algorithm, we need to initialize some of the parameters. So unless we initialize those parameters, the algorithm will not be, it is not possible to run those algorithms. But in case of PSO, whatever value you give 1 lakh, and if you give 10 lakhs or 1 crore or maybe 1 or 0.01. So if you start with that particular, say for example, your global best or the optimum value is 263.2. Now you are starting your initial point you have taken, that is 1 crore. So the algorithm will reach to this 263.2, or similarly, if you are starting with a 0.001, so the algorithm will again, it will convert to 263.2. So that is the beauty of this particular algorithm. It is not dependent on the set of the initial points of compared with the other optimization techniques. So it is conceptually very simple. It is very simple algorithm. Now, disadvantages of the PSO algorithm. So what are the disadvantages? First is the PSO algorithm suffers from the partial optimism, which degrades the regulation of its speed and direction. Okay. So there are certain difficulties. Every algorithm, it has some disadvantage. There is no such algorithm which is free from any kind of disadvantage. There is because any soft computing techniques, it is basically adapted in such a way so that there is a possibility that the algorithm is improved from the previous version, whatever version is available. So nowadays, this soft computing application, there is a continuous research is going on this particular area, and this is the emerging area where the peoples are working. So everywhere, in every problem, there is a difficulty, there is a disadvantage. So this algorithm also suffers from the partial optimism. And the second is the problems with the non-coordinate system, for instance, in the energy field. So there are certain fields where three-dimensional space is there. In three-dimensional space, it is because this PSO algorithm, it is applicable for the two-dimensional space. For three-dimensional or more dimensional space, there will be, for non-coordinate system, there will be a difficulty or the disadvantage we can observe. Any doubt on this particular part? Any confusion from anyone? Anyone? Okay. Have you understood? Hello?
Yes, sir.
Any doubt?
No, sir.
Now, next is the empirical analysis of the PSO characteristic. So now we'll see that there are certain disadvantages of the PSO. Okay. So if the movement of the particle in such a way that it may reach to the boundary surface of the particular search region. Okay. So sometimes what will happen, the velocity of movement of those particles or their velocities are such a high value, so it will reach to the boundary surface of the search region. So sometimes it will overcome that boundary surface. So we need to clamp, we need to basically make those particles within the search space. So that's why there are certain techniques are there by which we can actually make those particles within the search space. So every algorithm, it has some two kinds of properties. One is the exploration, another the second is the exploitation. So exploration is the basically it is explored. We'll discuss in detail how this exploration and exploitation it is actually done. Okay, exploration means it is a global search, and exploitation means it is a local search. Okay, explore means for a wide region we are basically exploring where is the actual solution is available. But exploitation means you got some hints of those solutions. Okay, those problems, there is a problem and the solution is located within that search space. Now, to fine tune where is the exact location of that particular solution, we have to do the exploitation step. Okay, so this chapter basically discusses a number of modifications of the basic PSO, how to improve the speed of convergence, means how we can make this algorithm more faster and faster. To control the exploration and exploitation trade-off. So there is a trade-off, which if you are more thinking or if you are more weightage on the exploration, so you are basically exploring more on the global search. If you are making a more stress or more weightage on the exploitation, basically you are concentrating on the local search. So we need to trade off. Trade off means a balance between the local search and the global search, or We can say that is a balance between the exploration and exploitation. Now, to overcome the stagnation problem or the premature convergence, the velocity clamping technique, boundary value problems technique, the initial and stopping conditions, which are very important in the PSO. We'll see those things in detail, that what is this those techniques, okay, by which we can make those values within the search space. Now, first is the rate of convergence improvement. So, how we can make this computation speed faster, more and faster and faster. So usually the particle's velocity build up too fast and the maximum of the objective function is fast. So normally the velocity of the particle is too fast. So it will move in the search space in a very faster rate. Okay. So in PSO, particle's velocity is very important since it is the step size of the swarm. At each step, all particles proceed by adjusting the velocity that each particle moves in every dimension of the search space. So it will move in every dimension of the search space. So there are two characteristics. One is the exploration and second is the exploitation. The exploration is the ability to explore different area of the search space for locating a good optimum, while exploitation is the ability to concentrate the search around a searching area for refining a hopeful solution. So that just now I have told you that exploration, it is basically your global search where you have a good solutions. You don't know where is the actual solution is located, but probably you are identifying a possible area of the search space and you are guessing that some possible solution will be available on that particular search space. But the exploitation, it is the fine tuning. You have already guessed that particular location. Now you need to fine tune or you need to exactly find out what is the solution. So that is basically your exploitation. So exploration, it is the global search, and exploitation, it is the local search. So to fine tune where is the actual solution, it is available. So therefore, these two characteristics have to balance in the good optimization tech algorithm. So when the velocity increases to large values, then the particle's positions update quickly. So this is very, very important. So if your velocity increases to a very large value, so the previous velocity will be added with the particle's positions, so your movement will be very fast. So basically your velocity of the particle of any optimization technique, that is very, very important, and that we need to control very, very cautiously. So as a result, particles leave the boundaries of the search space and diverge. So you understand this thing, there is a search space and the particles are allowed to move within that search space, but due to this abrupt movement of the particles, there may be some chances when the particles will leave the boundary of the search space. So and diverge. So instead of converging, it is diverging. So you are not getting any solution. So this is a problem. So therefore, to control this divergence, particles' velocities are reduced in order to stay within the boundary constraint. So this is very, very important when you have got certain things which is very faster rate and it is overcoming, it is crossing the boundaries of the search space and it is diverging in nature. So we need to control the velocity of the particle. So the following techniques have been developed to improve the speed of convergence or to balance the exploration and exploitation trade-off and to find the quality of solution for the PS. So there are certain techniques. We can control the speed of the convergence. We can basically trade off between the exploration and exploitation and to find a quality solution in the Pso algorithm. Now, first technique, it is the velocity clamping. So to remove these difficulties, we have seen that due to this sudden movement of the particle from within the search space, the velocity is such a high value, it can cross the boundary of the search space. So to make this velocity within the this particle within the search space, there is some techniques are available. So one of the technique is velocity clamping. Now velocity clamping, it was first developed by Everard and Kennedy. So these are these two scientists. They are the pioneer of these Pso algorithms. They have actually developed this algorithm. So Everard and Kennedy, these two scientists. They have actually developed this algorithm. So first, introduce the velocity clamping. It helps particles to stay within the boundary and to take reasonably step size in order to come through the surface. So if your step size is higher, if your velocity is higher, so what will happen? The movement of the particle within the surface will be higher because they will be jumping at a higher rate. Okay, they'll be jumping at a higher rate. So either you need to control the step size or you need to control the velocity of the particles. So these two things are possible. So without this velocity clamping in the searching space, the process will be prone to explode and the particles' positions change rapidly. So this is a problem. Problem is the movement of the particle is too faster, so that instead of getting the actual solution, we are that may cross the boundary. So I will show you, let us say, with the help of some figure. Okay, I will show you. Just a minute. Huh? So let us consider this is your search space. And you are optimizing a function. Let us say fx equal to something x square plus sin x plus e to the power x into log x. And x is, it is varying between, let us say 100 to, let us say 5. We need to calculate where is the actual, we need to minimize this function. We need to minimize. So what will happen? Let us say, for example, the minimum value is located at a, let us say, for example, this is for example, it is located at, let us say, 202.1. So, for example, within the search space, this is 202.1. This is the actual value. We should get it. But you have a number of particles within this search space. You have a number of particles which is moving here and there. So they are actually moving. So let us say you have chosen the particle size is 10. Okay. The particle size is 10. So 3, 3, 3, 6, then 7, 8, 9, and they have started actually. They have started. So what will happen in the next step? So next step, this is, let us say, next step, the same search space, but the movement of the particle is such, what will happen is, this is the actually global value, that is the 202.1. But they are actually moving in a direction in such a way, this is the direction. Okay, 3, 2, 5, 2, 2, 4, 7, 8, 9, 10. Let us say this is the position of the particle. Now, in the next iteration, this is the, let us say, so this is equal to t equal to 0, this is t equal to 1, next iteration cycle, this is t equal to 2. So, what will happen? This is, let us say, the original 202, we should get this value, okay? But the particles are reaching at this surface, 3, 4, 5, 6, 7, 8, 9, 10. So they are reaching the boundary surface. So instead of getting this original or the actual value, the particles, because of the high velocity and step size. So both the things are important. Because of that, the particles may cross this boundary. There are some chances the particles may cross this boundary. So in order to control how to make these particles within the search space, because if these particles are moving out of this boundary, we'll not never get this solution, because this is within search space, but the particles is moving in some other direction. So ultimately, if that is the problem, we should limit the movement of these particles within this search space. So that is the basically velocity clamping. This technique is useful because of that reason. So that's why this velocity clamping technique is applicable. So without this velocity clamping in the searching space, the process will be prone to explode and the particles' positions change rapidly. It will reach to the surface and it may basically cross the boundary also. So maximum velocity controls the granularity of the subspace by clamping velocity and creates a better balance between the global exploration and the local exploration. So we need to control the balance between these global exploration and the local exploration. Okay, so this is the initial position, this is a new position, and this is the new position using the velocity clamping, and Xij t plus 1 using the velocity clamping. So this is without and this is with. Okay, so that means we'll see that if really we implement this velocity clamping, there is an improvement in the algorithm, and the particles will not cross the actual boundary of the subspace. So if the maximum velocity is too large, then the particles may move erratically and jump over the optimal. So we have seen that thing. So if the movement of the particle is such, it will move at a very high speed, high velocity. So in those cases, it will cross the boundary. So that is not basically acceptable, or the objective is not will suffice. So in those cases, we need to do a kind of balance so that the particles will lie within the subspace. So on the other hand, if it is too small, the particle's movement is limited and the swarm may not explore sufficiently, or the swarm may become trapped in the local optimum. So there is another side also. So if the step size and this velocity are very small, so very small means, so that means if the movement of those particles are very small, so there will be some chances that basically those particles will not move in the at a higher speed. Okay, so we need to do a balance between the global and the local side. So this problem can be solved when the maximum velocity Vmax is calculated by a fraction of the domain of the subspace on each dimension by subtracting the lower bound from the upper bound. And basically how we'll implement this velocity clamping. Velocity clamping, it is Vmax equal to epsilon into Xmax minus Xp. So we know every particle, it has some Xmax value and it has some Xmean value. And epsilon is basically constant. So by epsilon value, it is between 0 to 1. So it is a random number. So if you can make your velocity within the subspace, what will happen? You see, I will elaborate you this thing. So, for example, if you take any number, okay, if you take the x max equal to 10 and x mean equal to, for example, it is 2. So you have a function, let us say fx, and it is x square plus 1. And the value of x max means x is between 2 to 10. Okay. So if you choose a velocity clamping, that means velocity, if you are applying this, so this is x max minus x mean, what will happen? So epsilon is a random number. Epsilon, it is the basically random number which is between 0 and 1. So, for example, if you are writing epsilon equal to rand 1 in MATLAB, what will happen? It will give some value. For example, it is 0.7. So 0.7 into 10 minus 2. So this is 0.7 into 8. So it is how much? It is 5.6. So you will get all the values of this velocity which will lie between 2 to 10. This is the beauty of the calculation. So that means there will not be any chances that the velocity will be too high or it will be too low. It is basically clamped between the minimum and the maximum. So how to clamp this velocity? Is it clear? Is it clear?
Yes, sir.
Okay. So there is another problem when all the velocities are equal to the maximum velocities. So if it is all velocities are coming at this maximum velocity. So at that time, what will be the problem? Problem will be you cannot further update because it has reached to the maximum. When it has reached to the maximum, then there is no chances of getting the updation. To solve this problem can be reduced over time. The initial step starts with a large value of Vmax and then it is decreased it over time. So if you are getting some problem regarding in your problem while solving this problem, if your velocity value it is reaching to the maximums, we need to decrease it with over a step. Okay. So the advantage of the velocity clamping is that it controls the exploration. It basically controls the explosion of the velocity in the searching space. So finally, Vmax was first introduced to prevent explosion and divergence. However, it has become unnecessary for convergence because of the use of the inertia weight omega and the constriction factor lambda. So we know this velocity clamping techniques, it is very, very popular, and we know how to solve this problem when the particles are basically reaching to the boundary, and when it has reached to the boundary, how to make those particles within the search space. So there is a technique which is known as the velocity clamping. So what is velocity clamping? We know that. Okay. Now, apart from this technique, we have something it is known as the inertia weight technique, and there is another technique which is known as the constriction factor approach. So if we apply this inertia weight and the constriction factor approach, so there this velocity clamping it is basically unnecessary. That is basically not required in this technique. So this problem it is also mitigated with the help of this inertia weight technique and the constriction factor approach. So we'll see that what is this inertia weight technique. Now the inertia weight denoted by W is considered to replace Vmax by adjusting the influence of the previous velocities in the process. And it controls the momentum of the particle by weighting the contribution of the previous velocity. So here we know that every particle, if you can think of the velocity updation equation, so the first part Vij plus 1, it was equal to Vij plus the personal part, personal experience part plus the social experience part. So initially it was only Vij. So now we want to multiply with some weighted factor W. So this weighted factor, it is basically controlling the momentum of the particle by weighting that contribution of the previous velocity. That means we are weighting that particular function. And why we are weighting? Because we'll get a better kind of result. That the computation speed will be more faster, the chances of getting local optima or the chances of basically velocity clamping is not required. Okay, so those things are basically useful, and that's why we are actually applying this inertia weight technique. Now the inertia weight W will be at every step be multiplied by the velocity at the previous time step, that is Vij. So therefore, the G-based Pso, the velocity equation of the particle I with inertia weight changes from the equation Vij plus 1 equal to W into Vij plus C1 into R1 T into P-based I minus Xij plus C2 into R2 into G-based minus Xij. See, this was actually originally it was there. Only the W term it is introduced. So the new contribution in this particular inertia weight, it is basically the W, the additional term is incorporated in this particular step. So the inertia weight was first introduced by the Shi and Everard in 1999. So again, that Everard and Shi, they are the pioneer of this Pso algorithm, and they have actually developed, they have actually modified, they have improved this Pso algorithm at a much higher steps. Okay. So to reduce the velocities over the time or iterations, to control the exploration and exploitation abilities of the swarm, and to convert the swarm more accurately and efficiently. So what was the task? Why we have introduced this W? The reason is we'll get a better control over the exploration and the exploitation abilities of the swarm, and to convert the swarm more accurately and efficiently. So this is another purpose. Now we'll see that what is the actually impact on this W. If this W is very, very greater than 1, if it is very small, or if it is W is 0. So what will happen to the movement of this velocity? So if W is very, very greater than 1, then the velocity increase over time and particles can hardly change their direction to move back towards optimum and the swarm diverges. So this is not desirable again. So omega value, if it is very, very greater than 1, that is not actually desirable. But if omega is very, very less than 1, then little momentum is only saved from the previous step and quickly changes of direction are set to in the process. So again, it is not a desirable kind of thing. If omega is very, very less than 1, so very little momentum will be there. So because ultimately you have introduced W to make a balance between the exploration and exploitation, but when this omega value, if it is very, very less, so the step size and the ablation process of the algorithm, it is basically not useful for implementation. Now, if omega is 0, then particles velocity vanishes. So omega 0 means there is no component. This component is 0 totally. This is 0. So this has no impact. Only these two components will be present. So that is not again useful. So particles velocity vanishes and all particles move without knowledge of the previous velocity in each state. So what will happen? So previously you had a something velocity. If you are making this term 0, so the particles will not remember what was the previous velocity of that particular particle. So that is not desirable because based on the previous experiences, the particles is moving in the subspace. So the previous experience is very, very important to update the position of the particles to the next level. So what has to be done? So if omega is very, very greater than 1, then there is a problem. If omega is very, very less than 1, that is also problem. Omega is 0, that is also problem. So what should we do? So to solve this problem, we have certain things to understand. So the inertia weight can be implemented either as a fixed value or dynamically changing. So there will be there are two maybe alternatives. First is either it should be a fixed value or we can dynamically change. So dynamically change means maybe from a very higher value to the lower value at each iteration steps, the particles, the omega value will be updated from the highest to the lowest. So each cycle, the omega value will be updated. So initially it will be very high, and as the iteration cycle will process, let us say further it is processed, so the omega value gradually it is decreased. So it is linearly decreasing kind of function. So the initial implementation of used a fixed value for the whole process for all particles, but now dynamically changing inertia values is used because of this parameter controls the exploration and exploitation of the surface. So initially what is happening actually at that time, the omega value, it was kept a fixed kind of thing. So fixed kind of thing, it was found that fixed kind of thing, we are not getting any improvement, or let us say the balance between the exploration and the exploitation is not also useful. So finally, it is actually found in the research that if we control this omega value in a dynamic way, so the balance between the exploration and the exploitation will be actually more suitable. So usually the larger inertia value is high at first. So just now I have told, so inertia value at the initial state will be very high, and which allows all particles to move freely in the surface at the initial steps and decreases over the time. So over the time period, it is gradually decreasing in nature. Therefore, the process is shifting from the exploratory mode to the exploiting mode. So what will happen as we process the iteration, as the iteration cycle will actually move forward. So the algorithm will be more tuned towards the exploratory mode rather than the more tuned to exploiting mode rather than the exploratory mode. So global search will be done at the initial phase of the iteration, and local search will be done at the later stage, or the maybe when maybe a few steps, which is basically ending the iteration cycle. So this decreasing inertia weight W has produced good results in many optimization problems. So this is the basically found suitable. So to control the balance between the global and the local exploration, to obtain the quick convergence and to reach an optimum, the inertia weight whose value decreases linearly with the iteration number is set according to the following equation. So finally, it was resolved that I have told you that from a very high value initial value to a lower value, the basically omega value it is updated. So how the omega is updated? Omega t plus 1 equal to omega max minus omega max minus omega mean divided by t max into t. dB. So where omega max is greater than omega mean. So omega max and omega mean are the initial and final values of the inertia weight respectively. Tmax is the maximum iteration number and T is the current iteration. So this is the basically range omega max and omega mean. So commonly the inertia weight decreases linearly from 0.9 to 0.4. So the omega max value is 0.9 and omega mean value is 0.4. So the range is 0.9 to 0.4. It is at each iteration cycle, basically, it will be updated. So the inertia weight technique is very useful to ensure convergence. However, there is a disadvantage of this method is that once the inertia weight is decreased, it cannot increase in the swan needs to search new areas. So this is the basically drawback of this particular technique, the inertia weight technique. So when you are starting with a very high value and gradually you are decreasing it. So what will happen? This decreasing means if we have to explore more or any swarm needs to explore more, so there is no chance that you can go back. So that is the disadvantage of this particular inertia weight technique. So any question from anyone? Any question? Hello?
No, sir.
Okay, fine. So thank you. I think I need to take your attendance just a minute. Okay, thank you. We'll close this meeting. We'll meet in the next class. Thank you.
Thank you, sir.